Dear students, today in this video we will see how to construct the matrix of a linear function. So let us suppose we have two spaces. Today we will talk only about the spaces Rn and Rm. Let f from Rn to Rm be a linear function. Linear function. By linear function, you know what we mean. Actually, we consider Rn and Rm as vector spaces over R, over the field of real numbers. And then, when we say f is a linear function, we mean that is. So I can say that is f of alpha of x plus beta of some y is equal to alpha of f of x plus beta of f of y for every x comma y belongs to Rn and alpha comma beta in the field R. This is actually the meaning of linear function. You can also call this as a linear transformation, where we will focus only on this Rn and Rm as linear spaces or vector spaces, you can say. When we simply consider these as the sets with this structure also there, space structure also there, then by a linear function we mean a function f from Rn to Rm satisfying this condition. Now we will see how we can write this linear function in terms of a matrix. You might have seen then this construction of matrix for this linear function in the linear algebra course. Now what we do for the construction, we first of all choose the basis of Rn and Rm. Here we will consider Rn and Rm as vector spaces over the real field R. So I suppose that B is equal to E1, E2, so on, En, and B dash be equal to E1 dash, E2 dash, so on, Em dash be the basis of Rn and Rm as vector spaces over R. When we consider these as vector spaces over R, we will choose this as a basis of Rn and this one as a basis of Rm. By a basis, you know, we mean a subset of Rn which is linearly independent and which spans this Rn. Every element of Rn can be expressed as a linear combination of these. Every element of Rn can be expressed as a linear combination of these. But in this case, this is a standard basis. In fact, this is n tuple in which the first component is 1 and all others are 0. This is again n tuple in which first is 0, second is 1, again all other remaining are zeros, and so on. But each of these is n vector because these are the elements of Rn. Similarly, each of these are m vectors. This is m tuple. First component 1, all other m minus 1 remaining components are 0, and so on. And there are m elements in this basis because this is m dimensional space. Now how to construct, what is the technique for construction of the base, this matrix representation of this one f, this linear function f? What we do, we evaluate this f at each point of this basis B. We calculate the image of E1, we calculate the image of E2, we calculate the image of En. When we calculate the image of E1, I get f of E1. Under some formula of f, when f will be given explicitly, you can calculate this explicitly what the image is. But still here I can say f of E1, since f is a transfer mapping from Rn to Rm, so I can say f of E1. F of E1 is the element of Rm because it goes from Rn to Rm. So this is the element of Rm, but Rm has this one as a basis, therefore every element of Rm is expressible as a linear combination of these elements. Therefore this f of E1 can be expressed as a linear combination of these. Means I can write this as alpha 1 1 E1 dash plus alpha 1 to e2 dash plus so on plus alpha 1 m e m dash. F of e2 is equal to alpha 2 1 e1 dash alpha 2 to e2 dash plus so on plus alpha 2m em dash, then so on, then f of last is en vector, that will be alpha of n1 e1 dash plus alpha n2 e2 dash plus so on plus alpha of n m e m dash, where alpha ij, when we express this as a linear combination, the scalars in the brackets are always the field elements. We call these as scalars, but these are the field elements. So these will belong, alpha ij's will belong to field R. The underlying field in this case is the set of real numbers. For every one, this I greater or equal, less or equal I, less or equal to what? Less or equal n, and first subscript, and 1 less or equal j, less or equal to n. So this is the expression for each of these images. Now, what is the matrix of this F? We simply take these scalars in this expression. Alpha 1 1, alpha 1 2, so on, alpha 1 m. Similarly, alpha 2 1, alpha 2 2, so on, alpha 2 m, and so on, all these. The matrix of this F with respect to these two bases will be the transpose of this vector alpha 1 1, alpha 1 2, alpha 1 m. The first column of the matrix is transpose of these scalars. Transpose of the vector following with these scalars is the second column, and so on. That will be the matrix representation of F. Okay, let me write the matrix representation of F. If I denote this by F from B1 to B dash, I can say. Sometimes we call this as a transition matrix from matrix B to this basis B to basis B dash. So its value is, by definition, the value is alpha 1 1, alpha 1 2, so on, alpha 1 m, alpha 2 1, alpha 2 2, so on, alpha 2 m, and so on, alpha n1, alpha n2, so on, alpha nm. Of course, this is m cross n matrix. This we call as a matrix of linear function f with respect to the bases b and b dash. Why we use these symbols here, b and b dash? In fact, when you change the basis of the corresponding space, the matrix also changes. Of course, for different bases, these matrices have a relation. I will not go in that detail. Simply, we use b and b dash for the reason that this is a matrix with respect to these bases. When we change the basis, we get some other matrix. So this is the matrix representation of this F. Now, if I denote this matrix by, if A is the matrix F from B to B dash, then my F is given by, then F of X will be equal to A of X. Means you can construct back the linear map or the linear function. Actually, you had F, you constructed the matrix representation of F. Now I use the matrix representation of F, I can get back that very linear function F, where in this case X is the point of R n. Of course, here I mean here the comma vector. It hardly matters whether you will represent the elements of Rn in terms of or in rows. You write m tuple or n tuple in a row form, or you write the n tuple in the form of a column. In this case, I will write column so that the matrix multiplication is well defined, because I have here, this is A is m cross n, and this x is, then when I write it in column, I get n cross 1. So the product will be m cross 1. But m cross 1 means m rows, m cross 1. M rows and only one column means you can say m vector. That m vector will belong to Rm as expected, because f is a function from Rn to Rn. Okay, let me take the example to illustrate this thing. Example. Let me choose m, say 3, and m is equal to 2, and define f from R3 to R2 by f of x, y, z. Say some linear map, I can define this to be x plus y and y plus 3z. For every x, y, z in R3. You can verify this is a linear map. You can see f of alpha of this vector plus beta of some other vector will be alpha of this vector plus beta of corresponding second vector. So this is a linear map. I want to construct the matrix of this one, this f. For that I had to choose the basis of R3, I had to choose the basis of R2. Remember, in this matrix representation of linear functions, since we are dealing with the differentiation of vector fields or differentiation of, in fact we are interested with the calculus of vector fields or scalar fields, so I will always choose the standard basis. For general basis you can go in the linear algebra course, you can see we can change the basis, we get the corresponding matrices. So I will choose here the basis for R3. Let B for R3 is standard basis, that will be 1 0 0 0 1 0 0 0 1, and for R2 B dash will be 1 0 and 0. These are precisely the columns of identity matrices in the corresponding spaces. Now how to construct? As we have seen, we will calculate the value of this linear function at every point of the basis B, and all those values we will express as a linear combination of elements of B dash. For instance, when we calculate f1 0 0, the first basis element, by definition of f, you can see here it is x plus y, so I have 1 plus 0, then I have y plus 3z, so I have 0 plus 3 into 0, that means 1 comma 0. Now this 1 comma 0 I have to express as a linear combination of these, so it will be 1 times 1 0 plus 0 times 0 1. That's quite obvious because this is standard. In this case it's easy to calculate the coefficients in the linear expression, linear combination. So when we calculate f of 0 1 0, I get sum of the first two, then first plus third times second plus third times third, as per the definition. This is 1 1. This will be 1 times 1 0 plus 1 times 0 1, as a linear combination of these vectors. Then f of 0 0 1 will be, by definition, it is 0 plus 1, then 0 plus 3 into 1, this is 1 0 plus, sorry, it says 0 plus 0. x plus y, then 0 plus 3 into, so it will be, here it will be 0, then 3. So this is 0 times 1 0 plus 3 times 0 1. You can see. So these are the values of these images of basis elements. So what's the matrix? Therefore matrix of f, linear function f, from B to B dash, or transition matrix, is here. Just take the transpose of coordinate vector. Coordinate here is 0, 1 and 0 for the first, 1 and 1 for the second, 0 and 3 for the third. So it will be 1, 0, 1 and 0, then 1 and 1, 1 and 1 as columns, 0 and 3. Its order is 2 cross 3 because the map goes from R3 to R2. Remember, the order of transition matrix is dimension of second space multiplied by dimension of the first space. So this is the matrix representation of this very linear map. Now I want to see if this is a representation in another structure, like this is the space of tuples here. That very R3 is a space of 3 tuples, R2 is a space of 2 tuples. This is expressed as a its notation is an ordered pair. But now I have written the same map as a matrix. This is just the change of notation. The effect must be the same. That is, if you apply f to any x, y, z, you get this thing. This should also give the same effect if we apply this to any vector in R2, in R3. So if I choose, let A denotes this very f of B, B dash, then this A must give me the corresponding f. I told you in the last, before this construction, I told you how we construct f. If we choose, if f is equal to, or you can say, if A is this, then the map f will be given by f of x is equal to A of x, where x is any vector in R3, where x belongs to R3. You can verify this. If you choose any vector, say I choose f of say 1, let me choose x, y, z, generally x, y, z. By definition of this f of ax, I have a 1, 1, 0, 0, 1, 3. Then I have x, x, y, z. I told you I will write this x as a column so that the matrix multiplication is well defined. Now if you calculate the value of this one, that will be this column, this row into this column, that's x plus y. Actually I get column vector, but I can write, I told you that this representation hardly matters whether you write in terms of rows or in terms of columns. So you can write this as y plus 3z after multiplication, exactly the same. So whenever you have a linear function, you can always write that in terms of a matrix. To study the properties of linear function, you can study those properties through non-analytic properties of linear function. You can study through the corresponding matrix representation.